Okay, I think we can start. So welcome everybody to this session on non-deterministic planning. So we have 4 speakers today and we have 20 minutes each. So the first talk is by Orit Davidovich, right? And it's going to be on going topological in multi-disk extended Markov ratio decision processes. So the stage is yours.
Thank you. Hi, guys. I'm Orit Davidovich from IBM Research. I'm really sorry I have to leave you shortly after the questions. My flight is rather early, and I'll go grab my cab right after. So today I'll tell you about how and why we use topological constructs to solve nonlinear optimization problem in MDP. As a quick overview, I'll begin presenting the basics of EMRDP theory, then bring in a topological perspective, and lastly present our algorithmic solution derived from both. So people here are familiar with MDP, with its finite state action space, transition probabilities, immediate reward vector, and initial state distribution. One seeks to optimize over stationary policies, considering either discounted or expected average reward models in infinite horizon. In extended Markov decision processes, we introduce a notion of total risk of a policy to inform actions. We pose a non-linear problem in which maximizing reward while minimizing risk is captured by that ratio. When omega equals 0, we're back at MDP. When omega equals 1, we get Derman's Markov ratio decision process introduced in 1962. One can say that EMRDP is an interpolation between these two extremes. However, EMRDP isn't just a formal construct. The Sharpe ratio from our investment portfolio management is located at omega equals half. There's a nice way to capture the total expected reward of a policy using its occupation measure. The occupation measure of a policy encodes the concentration of probability of an action at a state at the infinite horizon limit. The occupation measure allows us to linearize the problem concerning reward, and accordingly, we can introduce an immediate risk vector and use the occupation measure to linearize the problem concerning risk. Now, Altman in 2004 provided the necessary and sufficient condition for a measure on the state action space to be the occupation measure of a stationary policy. This is nice because it explains exactly how we can formulate EMRDP in terms of the occupation measure. However, there is a slight redundancy to Altman's formulation. We can go one dimension down. A nice feature of this reduction is that now we can work both with discounted and expected average reward models in one single unified framework. So here's how we formulate EMRDP in terms of measures on the state action space. As a constrained problem, we can get a constrained MDP reduction from this problem, and that's dependent on a risk value alpha, and allows us to solve the EMRDP. In our 2023 ICAPS paper, we introduced 3 major assumptions, and using those, we use discrete gradient ascent on the graph of deterministic and one-randomized stationary policies. These assumptions mean, 1, we require the uniqueness of the optimal policy. The other is the irreducibility of the MDP. And lastly, the strict positivity of the immediate risk vector. Following that paper, we wondered how we may enable a notion of action-dependent risk regarding some types of actions like investing in securities as inherently less risky than others, such as investing in the NASDAQ 100 index, by weighing them differently. More generally, we can ask how to incorporate multiple risk aspects. Posing the question for multiple risks, at least at the face of it, is rather easy. Replacing a single immediate risk vector with multiple vectors and assigning individual weights to each. And the same EMRDP occupation measure formulation and CMDP reduction applies with, this time, M risk values, alpha 1 to alpha M. This allows us to consider EMRDP as a parametric LP problem whose general form you see before you, with B being the parameter vector, which in our case is varying according to the M alpha risk values. In our case, under the assumptions we introduced, we have 3 key properties: full rank, we have feasibility whenever we can ensure the parameter vector B is within the positive span of the A columns. And lastly, this LP is also bounded for every B. Topology comes in using an old result by Walkup and Wetz. It's actually known in algebraic geometry circles because of its relation to tropical geometry. This result is known as the basis decomposition theorem. The result by Walkup and Wetz says that a parametric LP satisfying the properties I just mentioned gives rise to a conic triangulation of the positive span of the A columns, such that the top dimensional conic simplex provides a unique optimal basis for all B's in its span. The proof relies on complementary slackness and provides a necessary and sufficient condition for being a top dimensional simplex of the conic triangulation. Now, if you're unfamiliar with the notion of conic triangulations, let me do a quick overview. Here in this talk, we look into conic triangulations that deal with positive spans of vector configurations. A simplicial cone is a high-dimensional analog of the trihedral cone. There are 3 assumptions on the collections of simplicial cones to make them into a conic triangulation. The union, closure, and intersection properties tell us how we're allowed to glue simplicial cones together. And intuitively, what they really say is that we should glue them together nicely along their facets so they perfectly fit into the conic hull of the vector configuration. Now, when we take this conic triangulation and we slice it with the m-dimensional alpha plane, we constrain our problem. Topologically, what we get on that alpha plane is a convex m-dimensional polytope P with a triangulation of its own that replaces simplicial cones with their hypoplane intersections. The EMRDP objective then can be shown to be a quasi-convex function over each top-dimensional simplex in the P triangulation. And as a result, the objective defined over the convex P achieves optimum on the vertices of that triangulation. For m equals 1, this just becomes a subdivision of the interval between minimal and maximal risk, and that exactly coincides with the graph of deterministic and one-randomized stationary policies that we used for discrete gradient ascent in the single risk case. In higher dimensions, aggregated risk defined on the alpha plane is in fact concave. And we get a very nice foliation of the alpha plane into risk level sets. If we assume that the vertices of the triangulation fall on distinct level sets, which is something that happens with probability 1, then that induces a natural order on the vertices of the P triangulation by total risk. The figure is actually an illustration of that in the case when m equals 2. The key point of our solution is that this global order can be established locally using topology. So if you want a walk-away bottom line from this talk, that's really it. The instruments of topology help us turn a global feature into a local property. This is done in a recursive fashion. Just a sec, let me gather my thoughts. This is done again in a recursive fashion, utilizing the star operation of a vertex in a triangulation. The star operation of a triangulation vertex is the union of all simplices, top-dimensional simplices, incident to that vertex. Hence, we get locality. And then we take its vertices, excluding the star vertex. Now, coming back to the figure, here is how it actually works. We start from the minimal risk vector, U1 in this case, and we take its star. Now, apologies for the typos. These all should be used instead of V's. We consider its star, the star of U1, and that's just the bottom two triangles in the picture. And then we grab the vertices of that, excluding U1, so that we get U2, U3, and U4. Among those three, we take the minimal risk one, which in this case is U2, and then we take its star and consider its vertices that lie on the high, kind of like high risk side of the level set. And so on it goes. We continue in that process until we exhaust all vertices of the triangulation. This swipe over the triangulation vertices is fully programmable, which is expressed in our new multi-risk EMRDP algorithm. In line 7, you can see the next policy subroutine, and it captures the vertices of the star calculated using linear algebra means. And from what I've told you so far, we've actually just shown that the algorithm does indeed return the optimal policy for the EMRDP objective. And we can also show that its runtime is bounded polynomially in the size of the state and action space and exponentially in the number of risk aspects. And this result assumes a complete order is given on the actions determined by aggregated risk. This new algorithm can be demonstrated on the grid world problem. However, we need to introduce a notion of risk. And we chose risk for, or added risk for walking along the bottom and top boundaries and walking into the left and right edges. In the single risk case, we get a very nice convex Pareto frontier. However, when we degenerate the single risk vector into two, that Pareto frontier becomes highly non-convex. This demonstrates the leap in complexity as we transition from single to multiple risks, where the greedy approach on the policy graph no longer applies. Underscoring, I think, the non-trivial topology involved and how it becomes necessary to tackle this problem. Thank you guys for listening.
So we have time for questions.
Yes.
So curiosity, I'm trying to draw the connection with between your algorithm and like a standard algorithm for MDPs. So it's like your algorithm emulates some kind of value iteration or policy iteration?
Neither actually, yeah. So this is, as you can see, there's no like value or, value function or Q function involved. However, maybe some of you are more or less familiar with the fact that EMRDP has an LP formulation, and that LP formulation has a dual, and this is an extension of that dual.
Other questions?
Okay, so I missed the beginning of the talk. That looks pretty great, but so I was just wondering again so building on that former question. So there are algorithms for constrained MDPs that start from LPs and duals and things like this, and also make use of the notion of heuristic search. So they expand the variables. Okay. So if the states represent, let's say, the occupation measure of the linear program, they're going to start with a small set of occupation measure and then solve a linear program where the state at the frontier of the small LP are estimated using heuristic functions, and then it gives them an idea of where to expand to add more variables, like a bit in row or column row generation, to extend that LP row and column generation. And so with that, you expand a very small fraction of the whole LP. Do you think, again, having not seen the beginning of the talk at all, that these kind of algorithms could be extended to this more complex setting that you have?
I think yes, because certainly if we don't have to tackle the big LP problem, and in particular like the inversion of the kind of like the big matrix that we're working with for full solution, then that would be great, because in this case what we're really doing is at each iteration we have this matrix, and the size of that matrix is like the size of the state space by the size of the state space, and that can be really big and unscalable if we want to invert. So using techniques that would allow us to like concentrate on a subset of that would definitely help. Yeah, but I do think there's a synergy there. I think it can be made, to fit.
So maybe we have time for one last question. Okay, so we can thank the speaker so that I'm not going to miss.